Good morning. Today's lecture we will go through a new topic which is called power transformers. So what does transformer mean? And what's the benefits of using transformer? Let's recall this electrical connection system. We have a power plant for generation. Then we used to say we transmit the power for high voltages and extra high voltages, so we can make sure we can transmit the power for longer distances and lower losses. So the main reason for making high voltages is because we would like to make sure reduce the losses as much as possible. Then, after we go close to the load, we need to step down the voltages. And we step down the voltages in steps. So first step from high voltages to medium voltages. Then when you go closer to the load, from medium voltages to low voltage. Then how can we go from low to high, high to low, etc., which is using the transformer. We have a step-up transformer, like as we see in number 1, step-up transformer. Basically, will convert the voltage from medium voltages to high voltages. Basically, the power planets will be in 15 kilovolts, 13, 19, 20 kilovolts, something like that, up to 132 or 230, 400 kilovolts. Then in transmission substation, we have we should have transformer that convert from 400 kilovolt to 130 or 130 to 33, 66 kilovolt, whatever. Then the distribution transformer, basically, this will be converting the voltages from, I would say, like 33 kilovolts to 7.2, or convert the voltages from 33, etc., 11 kilovolts to 7.2. After that, we have the residential home transformer, which is that supply your home, the small transformer. So in other words, this is how the small transformer looks like this. So we see that there are several types of the transformers, but all of them, the main target is to make step up voltages or step down. That's the point, step up or step down. And of course, the higher power, the higher voltage will make it the higher size. So it will be bigger size whenever there is a high voltages, high currents, in other words, higher power. So you can see sometimes the rating of the transformers. Some of them can handle up to 2 megavolt ampere, some of them 500 volt ampere, etc. Like 20 kilo volt ampere, etc. So again, like there are several types of it. Then the transformer also can be either 3-phase or single-phase. And we have something called like biphase transformer. Basically, the transformer that's or the transformer that can produce more than one outputs. So we will discuss like something called 2 windings or 3 windings transformer later. But I would say like the transformer purpose, step up or step down, no matter what the scale it is. So all of them almost the same concepts, but again, the size, the design can be different. And sometimes there is a lot of challenges about the cooling of the transformer, especially when there is a high voltages or extra high voltages. So they used to use some type of sometimes oil to make it cool. Sometimes they are using fans for cooling. Sometimes mixing both. Sometimes they are using some gas, etc. So there are different things about it, which is not our scope. Our scope, let's focus here just a little bit about the overall concept of the transformer, which is basically step up or step down. And keep in mind that transformer is basically have its equivalent circuits. So let's go to the class notes here. This is some examples of the transformer. So we have some big transformers like what we see here. This is very big, what's called like power transformer. This is maybe as size as this room. And we have a small, like this used for a home residential area. But this is, I think it will be very small size, like smaller than the table. Then we have This is very small, used in electronics. It can be inside the boards, electronic boards. This one also is very small. We have this type of transformer. Maybe you can notice this for some large applicants. I mean large home applicants, not super large. So this can be used, for example, as an example, to convert 120 to 240. That's a roughly example about it. Then we have this transformer is being used for sometimes in electrical substation to measure for measurements. So this is sometimes called voltage transformer, and this voltage transformer basically converts the voltages from high voltages into a small, like for example from I would say 132 kilovolts into a small like 5-10 volts. Why I need to convert this like this? Because sometimes when I have the microcontrollers voltage range is very low, like from 0 to 5 volts, negative 15 to 15 volts, etc. Like if you're familiar with Arduino or the other thing, which is basically, those are very small scale. Then since I'm taking measurements from the high voltages, I need to isolate this from my measurements, from my control circuit. So basically, I need to take an indication about the measurements, but at the same time, I don't want this effect to my system. So I'm using this as type of instrumentation to measure the voltages. And we have another type like CT transformer. Basically, it's called current transformer. So basically, this is being used to measure the currents. And again, these two voltage transformer and current transformer, both of them are being used in large electrical substations for measurements. So I have an access to measure both the voltages and the current. Then I can estimate how the amount of power being go to this electrical substation. So again, those are, just for information, that there are many types of the transformers, but all of them around the same topic, which is step up or step down. Now, how is the transformer equivalent circuit will look like? Everything, no matter if they are looks different, but they are basically based on core from ferromagnet. Then there is a coil. So you can imagine this small transformer. There's a number of turns around the core. This is for primary side. This is for secondary side. Then we have a core around the core. Then even if you open that transformer, you will see the same. If you open the other transformer, you will see the same. But some of them 3-phase, some of them single-phase, whatever. So when you see 3 brushes here, 3-phase, this one is single-phase, this one is single-phase, this one is 3-phase. So whatever. I'm not going to go through 3-phase transformer. Let's just discuss the single-phase just to prove the concept. This course is fundamentals electrical engineering. This is not electrical machines. Then we will not go 3-phase. So anyway, basically you will see a core. And there is a numbers of turns in the primary side, numbers of turns in the secondary side. That's the equivalent circuits. So we try to be realistic, try to make the model something closer to the reality. So why I make it like as an inductor? Because if there is a ferromagnet material or a magnetic material and there is a number of turns around it, this is equivalent circuit to the inductor. Or this is actually as an inductor. That's why we have an inductor formula like this. Now, the transformer has different things. So basically we have this model, and this model is called 3-windings transformer. 3-winding transformer. What do I mean by 3 windings? It has 3 different things. 1, 2, 3. Like 1 primary, 2 secondary, or the vice versa. 1 secondary, 2 primary. Then we have another type, which is called 2-winding transformer. So the 2-winding transformer, basically it will include only 2, which is 1 primary, 1 secondary. So that's how it looks like. Again, we have one primary, one secondary. This is two windings transformers. Then, as an example of three winding transformer, which is the transformer that supplies to your home. So you can say like you have 7.2 kilovolts, then it will be here 120, 120, and if you mix both of them, it will be 240. That's as an example of three windings. Then other types like two windings, like when you convert the voltages from different level to another level, or like if you can use the voltage on high voltages or extra high voltages. So basically, for this course, we will focus more on power transformer. Basically, these transformers that we are using it to power up the devices. We will not discuss, go through transformers being used in measurements or in communications, signals, etc. Let's focus more on the power, which is again the transformers that are used to supply the power. Supply either home, supply a small device, supply city, like whatever. Then, sorry, I said city, not city.
Okay, I found this on the web for that.
I'm sorry. Okay, then you need to keep in mind something important, which is when you see this circuit, yes, we see inductors, we see two parallel lines. Those are indicating for the core, but keep in mind something which is important, which is the voltage polarities, current directions. The other thing, the dot location. Okay? So we need to have two assumptions that's very important. So those assumptions are based on the dots, such that you need to make sure the positive polarity will be on the dot side every time the currents flow into the dot side. This is a must. Sometimes, or most likely, you don't have, the circuit will not be given with the voltages, polarities, or current directions. As any electrical circuit analysis, what we used to do, we used to say, let's assume a voltage, polarities, and current directions, right? That's what we used to do. Then here, whenever you have the transformer, you need to assume your own voltage polarity, or your voltage polarity and current directions. How? The voltage must enter, the voltage must be, the positive side of the voltage must be at the dot side, and the current must enter the dots. This is a must. So these dots, the location of these dots are in purpose, and those are very important to look at. Then, how can we solve this? Basically, we have three equations that are very important. So we have the first thing, which is called the voltage equation. So it will be V1 over N1 equals V2 over N2 equal V3 over N3. Then the current equation, I1 times N1 plus I2 times N2 plus I3 times N3 equal to 0. Then equation 3, power equation, S1 plus S2 plus S3 equals to 0. If we have two windings, what should I do? It will be the same equation, but remove 3. So it will be no S3, no I3 N3, no V3 N3. If it is two windings. If it is three windings, just return it. Okay? So whenever you see two windings, forget about 3. So these equations, again, are very important and very essential in our analysis. So basically, when you do any circuit analysis, we will do Ohm's law, KVL, KCL, voltage division, current division, source transformation, whatever we used to do in the past. But whenever we go to the transformer, we need to use one of these three equations, or maybe all of them, maybe two of them. So these three equations are the tools for you, then you can use them whenever you need them. So N1, N2, N3 are related to the terms, number of turns. V1, V2, V3, the voltages. I1, I2, I3, the currents. S1, S2, S3 are the complex power. Let's assume, as an example, we have a two-winding transformer like this. And we have a dot here and a dot here. So before doing any analysis, please make sure to assign a voltage polarities and current directions. So let's assign a voltage polarities and current directions. For the primary side, where is the positive part must be? At the top, which is at the dots, plus minus V1. Well, where is the current direction? Into the dot, right? So here is I1. How about the secondary side? We will flip it because the dot will be down. So plus minus V2 bar. How about the currents? Must enter the dots. Okay? So make sure to be consistent with the dot side, okay? The current enters the dots, the positive polarity of the voltage will be at the dots. If you know this, and if you know these three governing equations, then that's it. We know how to deal. We know how to do the power analysis, complex power. We know how to do the AC circuits. Will be very similar to chapter 5 and chapter 7. But this is the additional thing. Any questions? Yes?
With the 3 windings, how come the dots were on the same side?
With the 3 windings, here is a dot. So if you assume, as an example, like the dot is here, then you will make plus minus V3, and you make the current go like this way.
So does it matter where the dots are with respect to each other across the...
Yeah, it doesn't matter. You need to make sure the current enters the dots, and the positive will be at the dot side. Other than that, don't worry about that.
Thank you.
You're welcome. Okay, so keep in mind this is the equation of the transformer. We will discuss the very basic, or which is, in other words, the ideal case. However, the transformer has its own inside inductance, and there is a small resistance with it. So there will be some losses will go through the transformer. These losses can impact the transformer, which is basically we need to have an equivalent circuit for the transformer. So basically, this is the simple case. Then there is more advanced case by drawing the equivalent circuit of the transformer. And that equivalent circuit of the transformer will be, the discussion will take longer time. We will not discuss it here, but I'm just letting you know that there is a more complicated model for the transformer other than that, but it will not be covered. This is not our scope. Okay? So the transformer, again here, the model, or basically there will be several type of losses. Sometimes when you go closer to the transformer, you will hear some noise like zzz, something like that. Even here, when you go to any small electrical substation or close to the electrical room, you will hear like this noise called zzz. It's called eddy current losses. And this is eddy current means because basically there is a core. So you can see the core, and there is a magnetic field going around it. And in the magnetic field, at the edge, you will see this type of magnetic field here. So this type of magnetic field will cause eddy currents. So these currents are recirculating currents. And this is something undesired. This something causes losses. Then you will hear this noise because of this. And this sometimes can cause the transformer to be heated. Then we have some cooling techniques. So of course, the higher loads, the higher losses you will see, then the higher noise you will see. So that's why sometimes you will see the noise is not a lot. It's not sometimes at some days the noise will be very very loud. So this is depending on how much the load we have. Okay. So this again is called eddy current losses, and this eddy current loss is something undesired, but it exists. We cannot control it. This is the nature. We try our best to minimize it, but it is what it is. So that's why the original equivalent circuit of the transformer, you will see some resistance inside it. You will see some inductance. But again, we will not go through it. Okay, it's time to do some questions. So, example number 1. Sorry. Given 3W. 3W means 3 windings. Transformer, rated 7.2 kilovolts, 120 volts, 120 volts, 50 kilovolts, 25 kilovolts ampere, 25 kilovolts ampere. It's very important. When you look at this, you need to know, is this voltage, is this current, is this apparent power, complex power, by looking at the units. So you can see 7.2 volts. This is what's voltage, right? 120 volts, 120 volts. This is actually the whole voltage. Then we have 50 kilovolts, 25 kilovolts, 25 kilovolts ampere. All of them volt ampere, volt ampere, volt ampere. This means this is real, reactive, apparent, complex. What do you think? Recall.
X.
Recall. Real power watts. Apparent power, reactive power var. Complex power volt ampere. Apparent power volt ampere. Okay? So look at here. We have only a number, 50 kilovolts ampere. So is this complex power? No. The complex power must be number and angle, or real part and imaginary part. This is not complex number. This is just a number. So it's what?
Apparent power?
Apparent power, exactly. So when you see this, try to write the information, that available information. We have the ratio V1, V2, V3 equals 7.2 kilovolts, which is times 10 power 3, 120, 120. Then the other thing, given information, S1, S2, S3 as a ratio, 50 kilovolts ampere, 50 times 10 power 3, 25 times 10 power 3, 25 times 10 power 3. Now the question says, find all of the ratios between all windings. We need to find the ratios. How to find the ratios? With number one, I'm going to say this is number one. Then we have number two. Number one, how to find the ratio? Let's go back to see the voltage equation. Voltage equation says V1 over N1 equals V2 over N2 equals V3 over N3. So we can say V1 over N1 equals V2 over N2 equals V3 over N3. I have the ratios, so what should I do? You can substitute V1 7.2, V2 120, V3 120, or you can say like V1, V2, V3 as a ratio equal N1, N2, N3 as a ratio. Therefore, 7.2 times 10 power 3, 120, 120 equals the ratio N1, N2, N3. Let's simplify it. Then we can say here 60, 1, 1 equal N1, N2, N3. As a result, we can say N1 over N2 equals 60. N2 over N3 equals 1. N3 over N1 equals 1 over 60. Something like this. Okay? Now the next thing, find the rated currents for all windings. Keep in mind something's called rated currents, not the currents. What does it mean? What's the difference between the currents or the rated currents? So basically, if I need to say find the currents alone without the rated currents, which is what's the current right now? Basically, I mean I need to find the angle, I need to find the voltages, I need to apply KVL, KCL, etc. But when you see rated currents as the word rated, this means I need to find only the magnitude or the maximum allowable currents. Maximum allowable current to maintain a safe operation. That's what does rated mean. Maximum allowable currents to maintain a safe operation. The transformer can work higher than the rated currents, higher than that, but it can work for a short period of time. If it's work permanent for higher than that, this will cause some damages. So it can work up to 30 minutes, 1 hour, higher than the rated, but not every time. While the rated currents, if it's work forever at the rated currents, this will maintain a safe operation, so there's no problem with that. So again, the rated means the maximum allowable currents. And basically, whenever we need to calculate the rated, calculate only the magnitude. You don't need to worry about the angles. While if we say calculate the currents, not the rated, well, then basically you need to calculate the complex number, which is real number and imaginary number. Okay, does this make sense? So please make sure to write this down so you can know what does rated mean. Okay, how to find the rated currents? How to find the currents? We know V, we know S, right? We know S as a magnitude, not as an angle. We know V as a magnitude, not as an angle. And we need to find I. Yes. Can we find it? Yes, we can. So basically, how we can find it? We can say S equals to V times I conjugate. But I need to find the magnitude. So basically, we can say S as a magnitude equal V as a magnitude times I as a magnitude. Then how to find I? Or I can say, since without bar this means a magnitude, so I can say S equal V times I. I mean, since there's no bar, this means it's only a magnitude. So I will be S over V. How to calculate the currents? We can say I1 equal S1 over V1. S1 is 50 times 10 power 3 over 7.2 times 10 power 3. So the answer will be 6.94 amperes. I2 equals S2 over V2, which is 25 times 10 power 3 over 120. Then the answer will be 208.33 amperes. I3 equal S2 over S3 over V3, which is 25 times 10 power 3 over 120. So it will be 208.33 amperes. Okay? Is this clear? Then that's the problem done. But keep in mind, there's a notice that you need to think about. I3, I1 associated with 7.2 kilovolts, right? I2 associated with 120 volts. I3, 120 volts. So what you can notice between these values? This is the high voltages, this is the low voltage side, this is the low voltage side. What you can notice? Look at the currents and the voltages.
Higher the current.
Exactly. The lower the voltages, the higher the currents. Why this is happening? Okay, do you know why? Yes, exactly, which is to equalize it. So basically, the transformer will not change the power, will not produce power from nothing, will not consume all of the amount of power. The transformer basically make voltage high or make voltage low. The power must be constant. We know P equal V times I. So let's assume this levels, like a water level. Let's make this water up, then what will happen to the other level? Will be down to maintain the same quantity of water. Then if you need to make the current up or make the voltage down, then the current will be up. Just imagine this like a water level. So the amount of water will remain as is. So what we are doing is just levelizing this. That's how you can imagine it. That's why whenever we deal with low voltages, you will see most likely high currents. Okay, so 208.33 amperes. Okay, will this go to your home? No, part of it will go to your home. How? Basically, that transformer will be responsible for supplying multiple homes. So 208, which is 208 amperes, this is the whole neighborhood sharing this amount of current on phase A. Then some others in phase B, some others in phase C. So this is the amount of sharing currents, total sharing currents. Okay? That's how we do this in real life. So I'm trying to go through practical things so you can just try to compare this, just like not going through equations and that's it. This is how to use the equation. Okay, so because the thing I understand, which is maybe after 1 month at the end of this course, you will forget most of the formulas, but the concepts will remain. So it's very important. Question number 2. 3-winding transformers that supplies 2 homes, which is the same as the previous one, or like the 7.2, 120, 120. Like again, this is the one that we have here. Then we have a loads SAB 2 times 11.6 plus J4 74, SAN2 4 plus J3, SNB 4 plus J0 kilovolts. So the question says, determine all of the currents flowing in the transformer, then all of the complex powers in the transformer. Okay, what should I do? We need to calculate I1 bar, I2 bar, I3 bar, and we need to calculate S1 bar, S2 bar, S3 bar. Keep in mind, it says all the currents, not all of the rated currents. It didn't say rated. It says all of the currents. Then the same for here, for the complex power, all of the complex powers, not the rated power. So that's something important. Then Look at the circuit. So most likely the circuit will be given. I'm not going to assume that you will memorize how is the electrical circuits of residential home will be. So that's how the circuit we have. Then most likely you need to assume the current directions and voltage polarities. Here it's given, then you can skip the one step. But in case if it is not, keep in mind here is the dot, dot, dots. The current enters the dots, the positive at the dot side. The current enters the dot, the dot at the positive side. So what should I do? The voltages for the primary side, 7.2 kilovolts, angle 0 degrees. V1, 120, angle 0 degrees. V2, 120, angle 0 degrees. So what do we have? We have SAN, we have SAB, SNB. All of them are given. So let's try to plan our answers. So how can I find the currents since we have SAN, IAN? You can say this is still 120, angle 0, 120, angle 0, 240, angle 0 degrees. We know the voltage, we know the complex power. How can we find the currents? S equal V times I conjugate, right? So we can find the currents, right? Okay, so we can, for all of these three, we can find IAB, IAN, INB. Okay, my target is to calculate I1, I2, I3. How can I find them? You can do KCL here, and you can do KCL here, right? So you can know IA, IB. How to know I2 and I3? I2 and IA are the opposite of each other. I3 and IB are the same as each other, so I2 will be negative IA, while I3 will be equal to IA. So I just calculated I2 and I3. How to calculate I1? Using the current formula of the transformer, right? N1 times I1 plus N2 times I2 plus N3 times I3. So here I'm just telling you how do we plan our answer. So we plan it, you can plan it within 30 seconds, 40 seconds, then let's start. So we know, do we have enough spaces? Let's start. We know S equal V bar times I bar conjugates. Therefore, we need to calculate the current. I will be S bar over V bar, all of them conjugates. Now, I need to calculate IA and IAB, INB. Basically, we can find it easy. We can say IAN bar equal SAN bar divided by VAN bar, all of it conjugates, which is going to be SAN given as 2 times 4 plus J3 times 10 power 3 because it's kilo, divided by 120, all of it conjugates. So you can do this analysis using the calculator and don't forget to write the conjugate. So the answer will be 83.33 angle negative 36.87 degrees and amperes. Then we need to calculate INB. INB equals to SNB divided by VNB. All of it conjugates. So it will be 2 times 4 plus times 10 power 3 divided by 120 angle 0. 120 angle 0 or 120 alone, this is the same. There is no problem with that. Then conjugates. Then it will be 66.67 angle 0 degrees amperes. Then the last current, which is IAB, will be SAB bar divided by VAB bar, all of it conjugates, which is going to be 2 times 11.6 plus J 4.74 divided by 7,200 angle 0, all of it conjugates. So it will be 104.43 angle, I think 20 something, 21. I'm not exactly sure about the angle, but it should be something closer to this amperes. Now, again, I'm not done yet. The currents, find the transformer, or the question says find the transformer currents, not the loads currents. What we did here is are the loads currents. How to find the transformer currents? Let's go back here. So we just calculated IAN, IAB, INB. How to calculate IA and IB? Let's do KCL at node 1 and KCL at node 2. So KCL at node 1, the sum of leaving currents will be 0. IA is entering, so it will be negative. IAN is leaving positive. IAB is positive, is leaving, which is positive. So KCL at node 1. The sum of leaving currents equal to 0. So it will be negative IA plus IAN plus IAB equals to 0. Therefore, IA will be the sum. IAN plus IAB. Then after doing the sum, it will be 18.62, 625, angle negative 28.72 amperes. Then the other thing, which is we need to calculate IB. Basically, look at here. Let's do KCL at node 2. IB is entering, INB is entering, IAB is entering. So all of them are negative. So the sum KCL at node 2, the sum of leaving currents equals to 0, then minus IB, negative INB, all of them bars, negative IAB, bar equal to 0. Then IB will be negative INB minus IAB. Then after doing the calculation will be 168.25, angle 166.4 degrees amperes. So now I just calculated these two currents. Then how to calculate I1, I2. Let's go back to the circuit to see is there any relationship between I1 and I2. I2 and IA are the opposite of each other. And the opposite means negative direction, or sometimes 180 degrees phase shifts. So you can say I2 equal to negative I3. How about I3 and IB? I3 and IB, I3 is going counterclockwise, right? Counter. IB, counterclockwise. So they are all in the same direction. So I3 and IB are equal to each other. So I will say as a result, IA or I2 equal to negative IA, while I3 equals to IB. So here, which will be 186.25, then the angle was negative 28 plus 72 plus 180 degrees, which will be 151.28 degrees amperes. Then IB, this is equal to IB 168.25, angle 166.4 degrees amperes. Keep in mind, when you write anything in polar, don't say negative 186.25 angle like negative 28 something. It was 128, 28.72. Don't say like this in polar. Okay? In polar, the negative sign must be written as an angle. So the negative will be as plus 180 degrees. Okay? I mean, when you box your answer, don't ever say the answer is negative 186 angle negative 25. So the negative will be exists in rectangular coordinates. There is no problem with that. But when you are in polar, the negative must be at the angle. How can you make this? How can you make sure to do the right thing? Basically, put in the calculator, if you want to just make sure everything's fine, 0 minus 186.25 angle 28.72. Put this in the calculator, then it will do the calculation for you. If you want to just make sure that you are doing the right thing. Okay, so now we just calculated I2, I3. How to calculate I1? Let's go back to the circuits. I1, which is at the primary side. Since there is a transformer in the middle, I know I2, I3, and then there is a transformer, then I need to use the equations associated with the transformer. What are these equations? Let's go back and see. We have three equations: voltage equation, current equation, power equation. What's the most suitable thing? Currents, right? We need to calculate the currents, then let's use the currents. Okay, so we can say using the current equation, we can say N1 times I1 plus N2 times I2 plus N3 times I3 equals to 0. Then we need to calculate I1. So I1 will be negative N2 over N1 times I2, negative N3 over N1 times I3. We know I2, we know I3, but do we know N1 and N2? Unfortunately, we don't. How can I know N1 and N2? We have the voltages. Let's use the voltage equation. So the voltage equation, we can say V1 over N1, or I can use as the relationship like V1, V2, V3 as a ratio, N1, N2, N3. So this is 7.2 kilovolts, 120, 120, or in other words will be 60, 1, 1. This is N1, N2, N3. Then I know the relationship. So let's go and substitute this here. Then we can say I1 bar will be negative N2 over N1, which is 1 over 60, times I2, which is, we calculated it as 186.25 angle, 151.28 degrees. Then minus N3 over N1, which is 1 over 60 as well, times 168.25 angle, 166.4 degrees. Then you can use the calculator to find the answer. So I think the final answer will be I1 bar. Yeah, we have a space there. We can say I1 bar will be 5.85 angle, negative 21.55 degrees amperes. Okay? Then the second part of the question is to calculate the power. How to calculate the power? We know V, we know I, V times I conjugate. So we can say S1 equals V1 times I1 conjugates, S2 equals V2 times I2 conjugates, S3 will be V3 times I3 conjugates. So V1, 7,200 angle 0, times I1, which is 5.85 angle negative 41.55 degrees, conjugate. Then V2, 120 angle 0, times I2, which is 186.25 angle 151.28 degrees. Then V3, 120 angle 0 degrees, times 168.25 angle 166.4 degrees. Don't forget the conjugates. It's very important. Do the conjugate first, then substitute this in the calculator. So you will get the answer. What were the answers? I think, do I have them? I do think I have the answers, but you can just substitute this in the calculator. You can find S1 will be a number, S2 will be a number, S3 will be a number. But keep in mind, you need to make them in rectangular coordinates when you box your final answers. Any question on number 2? Okay. Let's start on number 3. We might not finish it today, but let's start with it. A load is connected to 240 volts line, absorbs 12 kilovolt ampere at 0.96 lagging power factor, and it is connected to 7.2 kilovolts, 240. So when you read this, you see there's only 2 voltages. So basically this is 2 windings. 2 winding transformer. So when you do the relationship, there is no V3, no N3, no S3. Then the transformer primary side is connected to the voltage source. So this source is given. Then we need to find Vs. So basically this circuit says calculate Vs whenever you have this equation, this relationship, and you have the ratio. How to calculate Vs? Someone can say, okay, we have V1 as 7.2, then Vs equals 7.2 direct. The answer is that this is not always true. Why? Here, it's given as a rated 7.2. But it's not necessarily we are working on these conditions every time. So that's why we say calculate the source that's necessarily for the load to operate. If it says calculate the rated voltages, then you don't need to calculate anything. Say it's 7.2 and that's it. Okay, what should I do? The first step, assign a voltage polarities and current directions. Second step, start from the extra given information. So let's look at the circuit here. Let's assign a voltage polarities and current directions. We need to make sure, look at the dots. The primary side, the dots, the positive of the voltage will be at the dots. Then will be here is V1 bar. Then the current enters the dots, I1 bar. The secondary side, plus minus V2 bar. Then here is I2 bar, right? The next thing, start from the extra given information. So here also it's given the load voltage as, here is plus minus 240 angle 0 degrees. And we know the other thing, which is, we know the voltage or the power. We have 12 kilovolts. This is apparent power, kilovolt ampere, 0.96 lagging power factor. So we need, since we know the voltage, we know the power, then we can calculate the currents, right? So most likely, in order to calculate the currents in the right way, we need to assume a current of the load such that the current enters the positive polarity of the load. That's my target. Enters the positive polarity of the load. So I'm going to assume the current direction like this. After calculating IL, I can see the relationship between I2 and IL. If they're opposite, make negative. If they are the same, make it positive. So it's very important, since I'm going to start from the load, calculate the load currents, assume its own load currents. Okay? So we need to calculate IL first. How to calculate IL? We know the voltage, load, we know the power. So the power is given as 12 kilovolts and lagging power factor. Let's calculate the power in the right way, which is basically the power is S load given 12 kilovolts as a magnitude. Power factor load will be 0.96 lagging. Therefore, we will say S load bar will be S load angle plus minus cosine inverse of power factor of the load. Then it is 12 kilovolt, 12 times 10 power 3, angle positive. Why it's positive? Because it is lagging. Then cosine inverse of 0.96. So it will be as 12 times 10 power 3, angle 16.26 degrees and volt ampere. This is the complex power of the load. There is no need to convert this to rectangular because my target is not to calculate S, it's to calculate the voltage source. So keep it like this. Then how to calculate the currents? We know S load equals V load times I load conjugates. Then how to calculate I load will be V load over S load over V load. All of it conjugates. Then let's substitute the numbers. S load 12 times 10 power 3, angle 16.26. Divided by 240, and all of it conjugates. Don't forget to do the conjugate first. 12 times 10 power 3, angle negative 16.26, divided by 240. Then basically just 12 times 10 power 3 divided by 240 will make it 50, angle negative 16.26 amperes. So as a result, I load again 50, angle negative 16.26 amperes. This is I load. Now I need to compare I load with I2. They are the opposite of each other. Therefore, I2 equal negative I load. Negative I load, and negative means 180 degrees phase shift, so 50, angle 163.74 degrees amperes. Okay, is this clear? So let's stop here. Then next lecture we will continue on this example and do another example in power transformation.